This presentation will discuss nucleophilic attack reactions of aldehydes and ketones. We will particularly discuss sulfur and hydrogen nucleophilic reactions with aldehydes and ketones. The learning goals are as follows. You should know the conditions and be able to predict the products of sulfur and hydrogen nucleophiles with aldehydes and ketones. We will begin with discussing sulfur nucleophiles. So ketones and aldehydes can react with thiols virtually the same way as they react with alcohols. Again, we see in this example we have acetone reacting with two equivalents with a thiol to get a thioacetal and water. If you notice, this reaction takes place under acidic conditions, just as it does when it reacts with alcohols. In the second example, we have acetone reacting with a dithiol, same conditions as with a diol. Here, we need two equivalents of an alcohol. Here, we only need one equivalent because the thiol derivatives or groups are within the same molecule. Therefore, we only need one equivalent. And again, it's under acidic conditions. When you're reacting with a dithiol, you get a cyclic thioacetal, and again, our product is water. What I want you to notice here is that this too has to be under acidic conditions in order for this reaction to work. As we saw in the previous slide, an aldehyde or a ketone can react with two equivalents of a thiol group or one equivalent of a dithiol to get a thioacetal or either a cyclic thioacetal. We see here in this slide that thioacetals can be converted to alkanes when reacted with rainy nickel. So we see here this thioacetal is reduced to an alkane. What I would like to point out here is that this group is called a methylene group. So looking at these conditions, this allows for another method for reducing a ketone or an aldehyde to the corresponding alkane. So we see in this example here, we have this ketone. We see with the first reagents under acidic conditions, we have a cyclic thioacetal. We have a cyclic dithiol, and we would get the cyclic thioacetal. The second reagent, upon reacting that with rainy nickel, we see we've gone from a ketone to, in this case, a cyclic thioacetal, and then after the second reagent is added, we have an alkane. So now I would like for us, now that we know the conditions of reacting an aldehyde or a ketone with a dithiol or either two equivalents of a thiol, we can get a thioacetal under acidic conditions. And after we have that thioacetal, we can reduce that to the alkane. So I would like for us to predict, using these conditions, we can actually predict what the product will be when we react an aldehyde or a ketone with a sulfur nucleophile. So see here we have this ketone under acidic conditions, reacting it with one equivalent of this dithiol, and then reacting it with rainy nickel. We will get the cyclic alkane. Another example, again, the first reagent, as we see by reacting an aldehyde or a ketone with an alcohol, again, it must be under acidic conditions in order for this reaction to occur. And then Upon reacting it with Raney nickel, we will get the resulting alkane. Now that we have discussed sulfur nucleophiles, let's turn our attention to hydrogen nucleophiles. I would like for you to recall that aldehydes and ketones can be reduced to alcohols with the hydride source. Lithium aluminum hydride and sodium boron hydride function as that hydride source. These reductions are carried out or must be carried out under basic conditions. Remember that a hydride is a strong nucleophile. Therefore, if there's any acid in the reaction, you will have a simple acid-base reaction and you will not have your nucleophilic attack. Now let's discuss the mechanism. So again, this is done under basic conditions. So the first step is that our hydride H- attacks the carbon of the carbonyl group. And so we have our tetrahedral intermediate. So we get this alkoxide intermediate, and then it's followed by water, which we have our proton transfer, which results in our alcohol as our product. I would like to point out the reduction of an unsymmetrical ketone will form a new chiral center. Therefore, when you react lithium aluminum hydride with an unsymmetrical ketone, you will yield a mixture of stereoisomers. So now let's practice predicting the product for reactions of aldehydes with hydrogen nucleophiles. So here we have this ketone reacting with LaH and then followed by water. This will result in a secondary alcohol. If we react an aldehyde with LaH followed by water, it results in a primary alcohol. So in summary, in acidic conditions, aldehydes and ketones will react with two equivalents of a thiol to form thiolacetals. However, if we have an aldehyde or a ketone reacting with a dithiol, remember that both thiols are within the same molecule, therefore you only need one equivalent, so you'll get a cyclic thiolacetal. And again, if we go to the next step, meaning we will take the thiolacetal and react it with Raney nickel, then it will undergo desulfurization to yield the methylene group, or basically we will get the alkane. Remember, if we react lithium aluminum hydride or sodium boron hydride with an aldehyde or a ketone, we will get an alcohol. If it's a ketone, you'll get a secondary alcohol. If you're reacting it with an aldehyde, then you'll get a primary alcohol. I would also like to note, if you recall, in the mechanism for the reduction of an aldehyde or a ketone with lithium aluminum hydride, that first step is not reversible because hydrides are not good leaving groups.